Once again, I'm setting up. I hope you can see more or less. Okay, fine. Assalamu alaikum. Welcome to the continuation of the lecture. Now we began on 17.4. We talked about functions, mappings. Now we go to, and then we spoke about limits. But the limits is the same way we used to evaluate. You know, those things of L'Hopital's rule, you plug in values, you get the limit. It's the same thing you're doing. If it fails, you know, you have infinity over infinity, 0 over 0, indeterminates. You do the same thing you did for real numbers, okay? And that's how we've defined the same definition, so more or less we just change the variable, okay? Likewise here and there. So this is where we reached the last lecture. So I'll start from there. This is basically now we're bringing in the idea of derivatives or differentiability for complex value functions. So suppose the complex function f is defined in a neighborhood of a point z naught. Then the derivative of f at z naught, denoted by f dash of z at z naught, is given by the derivative of derivative at z naught equals what we used to do previously in calculus actually. I think it was calculus 1. That the limit as del z approaches 0 of f of z naught plus del z minus f of z naught divided by del z, provided the limit exists. That's the definition of derivative. And this is what we used to call by finding the limit by definition or by first principles in calculus 1. Okay. So again, here we go through these rules that you knew. These rules are the same. They don't change. Notation and rules of differentiations. When we say, you know, a function, now here is supposed to be w. W equals f of z or omega. Then the d dz of w is same as the derivative at z. This is just notation, okay, just what we mean. Then if f is differentiable at z naught, then f is continuous at z naught. The same in calculus. Then all these rules are the same. Constant, when you differentiate a constant, you get 0. When you differentiate a function multiplied by a constant, it's just differentiating the function, then you multiply by the constant. Sum rule is the same. You know, the derivative of the sum of two functions is, you know, the derivative of the individual functions. Product rule, the same, that you used to hold one constant. The derivative of a product of two functions is you differentiate this, you multiply by this, then plus, you hold this constant, differentiate this, and then you add. Quotient rule, the same thing, that, you know, the derivative of a quotient of two functions is you differentiate this, multiply by this, minus, differentiate this one, multiply by this, divide by the denominator squared. That's it. Chain rule is just now you differentiate. So the derivative of the function of a function is basically the derivative of the function as it is like that times the derivative of what you're dealing with, g dash of z. And finally, the power rule was just d dz of z power n. Here you just used to have x. So you just have n, you multiply by n, then you reduce the power by 1. For all z, now this is supposed to be for all z in C. Wow, this is a mistake I made there. It's supposed to be complex numbers, sorry. Okay? Those are the same rules, so please forgive me because I'm not going to repeat that. I mean, I just say you know already. Differentiate, find the derivative of this function. This is a polynomial of degree 4, and this is a rational function. So the derivative, so here you're just using power rule. So you differentiate here, you get 4 times 3 is 12, you reduce the power, you get 12z cubed minus 15z squared plus 2. Finish. There's nothing else to say. Then f of z equals z squared over 4z plus 1. How do you deal with this? Well, you just apply quotient rule. Quotient rule says you differentiate this, you get 2z, you multiply by 4z, minus, you differentiate this, you get 4z, you multiply by z, you get this. And then you just bring them together and you end up with that. So, power rule, quotient rule. The same thing you used to do. The same way you used to differentiate. Okay, differentiability. When we say a function is differentiable. So, here for complex numbers, it's a little bit tricky. It's a little bit more complicated. So, in order for complex function f to be differentiable at z naught, the limit must, so the limit, we say, by definition, this is a derivative. And so, if the derivative exists, then we can talk of, then, for the function to be differentiable, the derivative, this limit must exist or must give the same value from any direction. Now the thing is, for complex number, you can approach from different directions because you have many more variables, okay? So, I'm thinking of the imaginary, you have a line, you can approach it through the horizontal axis, the vertical axis, and so forth and so on. So example, show that f of z equals x plus 4iy is nowhere differentiable. This function is nowhere differentiable. So what we do, we apply the definition, this definition. So what we do, so since z equals x plus iy, then, del z will be del x plus I del y. So here when you're talking about del z, you're talking about, this is del x plus I del y approaching 0. So now, then, what we're given our function is f of x equals x plus 4iy. So that's f of z, which we will put here now. And then now we need, so this we need f of z plus del z minus f of z. As del z approaches 0, divided by del z. So f of z plus del z, what is it? F of z, we already said is this, we're given. So f of z plus del z is just where you have x, you add, so here you have, z. So this is x, will be x plus del x, plus 4i y plus del y, minus x plus 4iy. When you take the difference, you can see this x goes with the x, the 4iy goes with 4iy. So what remains is del x plus 4i del y. Then now you take the limit. So the limit of f of z plus del z minus f of z, this term, divided by del z, as del z approaches 0, this equals this divided by del z, but del z is this divided by that. So now this is a limit we need to check from different directions. So what do? Well, we just take limit from two different directions. So as del z approaches 0 along a line parallel to x-axis, the real axis, that means it's horizontal, so your del y would be 0. So this reduces to 0, and this reduces to 0, so you just have del x over del x, which would give you 1. Now, if we approach a line that is parallel to the y-axis, or the real axis vertical, the imaginary axis, the vertical one, this way, it means that x will not be changing, so del x would be 0. So we would have this thing, this becomes 0, this becomes 0, so you just have 4. And so now the limit here is 1, the limit here is 4 from different directions. So the limit does not exist because it's not unique. Hence, f of z equals x plus 4iy is nowhere differentiable. That's what you would do, ladies and gentlemen. Okay? Fine. We go to analyticity. Let me see how much of this is remaining. My goodness, just one moment. Analyticity, just 3 slides. But I don't want to rush you too much, because we'll talk about analyticity, example 5 continue. Yeah, we can look at it actually. Maybe we can finish. Okay. So analyticity. When we talk of analytic, we talk of, well, now this is a definition. So a complex function, f of z, is said to be analytic at a point z naught if, 1, it is differentiable at that point and at every neighborhood of that point. So you can have a function that is differentiable, but it's not analytic. Analytic requires more than differentiability at the point, that is also differentiable around the neighborhood of that z naught. That's 1. 2, the same complex function is analytic in a domain. You remember a domain, okay? Open connected set. We already looked at that in the section 17.3. So it's analytic in D if it is analytic at every point of D. Because for analytic, you need to be in the neighborhoods and so on like that. And then a function that is, a function is analytic everywhere in the complex plane. There's no exception. It's said to be an entire function. For instance, polynomials, complex exponential functions are entire. Rational functions are not entire because you see there is an exception. When the denominator is 0, there are those points the function is not differentiable and therefore it will not be analytic. It will not be entire. It's analytic around every domain that contains all the points except the denominator is 0. And then this function f of z equals modulus of the square of the modulus of z is differentiable at z naught but nowhere else. Now this was supposed to be an exercise in your book, but I did it here just to help you. So show that f of z equals square of modulus of z is differentiable at z naught but nowhere else. Solution, we do the same thing we did previously. What did we do? Well, we just take, z is x plus iy, so del z is del x plus I del y. Okay? So then f of z, modulus of this, by definition, what's modulus? It's just x, the real part squared, imaginary part squared. This is the z, so it's x squared plus y squared. Then now we need the limit, so we need f of z plus del z. So That's defined by modulus of square z plus del z. Now what is z plus del z? X plus del x squared plus y plus del y squared. Then we need to expand this. Expand this, and take the difference. So when you take f of z plus del z minus f of z, it's just this one you expand, you get this, plus all that, okay? Minus this one. So if you do that, you end up with this expression. I mean, f of z plus del z minus f of z equals 2x del x plus this squared and that. Now, this is what we need to find now. We apply limit. So when you take limit, as del z go to 0 of f of z plus del z minus f of z divided by del z is the limit of this divided by del x plus I del y. Now, this is what we need to approach from different directions to see what happens, okay? So, let's see what happens. So, if we take limit along two different directions, as del z approaches 0 along a line, again, parallel to x-axis is like this, so our del y will not be changing, so it will be 0. If there's no change, it's 0. So, we would have, in this thing, the del y, this is 0, this is 0. This is 0. So, what remains is just this plus this divided by this. If you cancel out the del x, you will have 2x plus del x. And so, if you take limit, you have 2x. Okay? Then, if you take the last one, actually, as del z approaches 0 along a line parallel to the vertical axis, del x will not be changing, it will be 0. So again, this relationship, this is 0, 0. So we remain with this plus this. Again, you cancel out, you end up with 2y. You can see 2x and 2y are not the same. So we get two different values for the limit. And we note that at z equals 0, the limit is 2x equals 2y equals 0. When z is equals 0. Which means at z equals 0, it is differentiable. The limit will be unique. But it will not be analytic, because it's only along that line. So if you take a neighborhood, it will not be differentiable around those neighborhoods. Hence, this function is nowhere differentiable. So we've answered the question that this is differentiable at z equals 0, but nowhere else. Okay, ladies and gentlemen, that is the end of the lecture. This is the end of the week. I wish you luck in the coming up midterm. All the best.